maybe we ought to look at the syllabus first. Let me stop this share. So that's the kind of thing I'll chop out stuff that doesn't need to be there and make it sequential. So I'm going to share the syllabus. Here we go. Now, all right, there's my name. I normally teach on the Raleigh campus in Beckley, but I like to come here. This is a nice campus. So, do y'all live around here? Okay. Okay. So, how are you going to WVU?
That's where we go during the school year. So we.
Oh, you live on campus. Oh.
We're both sophomores. We're going to be juniors, but we're both still coming home for the summer and being with family and doing vacations and things of that sort. So,
well, that's good. You don't have to
be like probably 10 minutes away, if that.
Good. It's not like, of course, driving an hour is not that bad because it's all 64. I teach a couple of chemistry courses at Southern in Logan during the regular semesters. That takes me hour and 45 minutes to get there. But I enjoy that too. It's nice to have, I don't know, the students are different at different campuses. It's odd. Okay. So for this course, I remember what I was going to say. So it's a good thing that you're in the programs you are, because if you were to take only the first semester and then go back to WVU and want to get the second semester, they might not jive. Yeah. I mean, they're supposed to be compatible, but you know, there's wiggle room. Okay, good. So this one's worth 4 credit hours and it's traditional. We meet for 4.5 hours. Your textbooks. Have you got your textbooks yet? Okay. I use Joel Carty's Organic Chemistry. You can get, you have 2 options. You can get a used copy for pennies, like this is a 3rd edition. You can get a 2nd edition, it'd probably work. Or a used 3rd edition may even be economical. But then to get practice in working problems, you have to work from that document. And those problems are numbered for the 3rd edition and the 1st edition.
So we do really need the textbook. We want to hear.
Well, the other thing about buying the textbook is if you get the textbook that has access to SmartWorks, which is their homework app from W.W. Norton, then I've never used that before with this textbook. And I thought what I would do this semester is build some homework into the course that the system will grade for me. That way it doesn't take up a lot of extra time. And it allows you, I've set it up so you can go in as many times as you want and correct your mistakes and hopefully, gain some expertise. And then the grade that you get on it is, rather than being part of the required grade in the course, would be an extra credit. And I would count all of your homework. At the end of the semester, would just average them together, and that would be worth an exam grade. So if you, it's in our bookstore, New River Bookstore. So if you buy it from them, you're guaranteed to get the right one. Or if you want to just be sure that you get, and I've got the ebook ISBN in here, and I've got the hardcover ISBN in there. Okay, those numbers right there. Yeah, there it goes. The ebook is probably the one that's going to have the homework access. And then you need to go to W.W. Norton and register with your code. And then once you're registered, I can go into the homework and add you to the class. Okay, if you run into any trouble, My contact information is the office phone. I don't know what's wrong with my office phone, but I never hear it ring. I think there's something. I get the voicemails when people call and can't get me. And those voicemails are converted into an audio file and sent to my email. So I get them pretty quick. But if you want to get to me even quicker, there's my cell phone number. And just text me. Unless you like to talk. If you like to talk, then I've got hands-free driving, so I can talk while I'm driving if you want.
So if you just had a preference, would you prefer us to get the online version, or would you say get the textbook version for the homework purposes?
Well, I'm not sure if the ebooks are usually cheaper. Yeah, and you can search them too. What do they do at WVU? Yeah.
I do a lot of ebooks.
If you're used to ebooks, and that sounds reasonable. In fact, I think the one in our bookstore, the New River Bookstore, is an ebook.
Is that located here on campus?
No, it's in the it's our website. Yeah. I can stop that share and show you. If you're not familiar with our website and how to navigate.
Not really.
We ought to look at that then. Yeah. Okay, so let me share. I gotta open my browser first. Okay.
And now everything we should need now should be on Brightspace. She called the other day and they told her that nothing would be available to us until 8 a.m. this morning.
That's true. Now, if I had been ready earlier as owner of the account, I can go in and open it up sooner. But I was playing hurry up, trying to get the course in shape. Because I haven't taught this course in 7 years. We haven't had enough students. So when you guys signed up, I said, well, most of the time, especially after COVID, students don't take this course unless they need it. So I said, okay, I'll do it.
Well, thank you. Yeah. We were worried that, I mean, we were assuming we would need a class size of at least 10 for them to consider having the course available, because we only knew of, like, she asked me, and she knew we were both taking organic, and she asked me if, maybe I would want to take it during the summer too, and I said, yeah.
If this were a university with a lot more overhead, that probably would be a rule. But I'm the only chemistry instructor at New River. So they've let small class sizes fly. I had 6 in my last general chemistry class. Website. Here it is. It's just newriver.edu. And okay, you guys don't see that stuff. I hate it. There's something about this browser. It's got a bunch of pop-ups that I can't get rid of. Aggravating. Okay, so to get to the course, there's a lot of stuff you can do in here, but let's go to the course first. Go to My New River. My New River. It's there. And you'll have a username, which for students, I think it's your last name _ middle initials. And then your password, before you change your password, I think it's your student number in the middle and N on one end, R on the other. I think that's the way it goes. If that doesn't work, then we'll have to talk to IT and get the skinny on it. Okay. Also, they have 2-factor authentication. And I guess you click on this problem with authentication option if you've never used it before, and then you probably set up with a phone number or an email address to send the code to it. I set mine for my cell phone. So 692. And then you can get into the sign-on portal. Yours is not going to have this many icons, but the one you want to look for is this D2L. That's Brightspace. Yeah, desire to learn. It's a Canadian company. Go figure. Okay, so then to get to your course, go to this little waffle right up here. And you'll only have the courses that you're signed up for. So this first one will be it. And then let me change over to be a student. So it'll look more familiar. There you go. Right. Okay. There are several things you can get out of using this program. One is class list. If you want to email the whole class, then you go in there and you can just click on it, identify like that. You can broadcast an email, or you can send individual emails. That's the way I communicate. Then to Zoom the class, I think if I go in here as Zoom, then you have all the Zoom meetings and you just pick the one that's current and sign in. If you have to, like if you can't make it to class and there's no lab that day, which would be maybe, let's see, today, the 29th, the 5th of June, 12th of June, 19th of June. Those days, if you need to, you can Zoom the class from here since we're not going to be having a lab, right? Not miss out on the live show. Okay. So let me go back over here. Okay. Everything that you're going to need, everything that I hand out in class is duplicated under content. In case your dog eats your homework or something, you have another copy. So if it's collapsed, then click on Start Here, Lessons and Resources, and then you're going to find the syllabus and my schedule there. So there's another copy of the syllabus. I'm not going to open it up because we already got it open. And there's my schedule. That tells you where I'm supposed to be during business hours. Okay. And there's, oh, I didn't give you a copy. Yikes. I thought I had copies made up. Hold on a second. I think I left that folder in the back. Let's just call it up. And you're welcome to print a copy if you want. This tells you I'm going to be on the Greenbrier campus Mondays and Wednesdays, of course, through those times. On the Raleigh campus, I'm going to be there to teach second semester chemistry on Tuesdays and Thursdays. But if you need a Zoom session, a private session, this is my personal Zoom account right here. We just click on that. And if we set up a meeting, then I'll already be there. And when you click on that, then we can, even if no matter where I am. But I don't keep regular office hours in the summer. But if you set up a meeting, I'll be there, even on the weekends. All right. So let's go back. Come on. There we go. Okay, back to content. All right, then the textbook information should be in here. This is the textbook information for this class. I think that's right. Let me look at it and be sure. Yeah, that's it. Oh, this tells us hardcover is $238. When I was a student, I thought $35 was, exorbitant. But the ebook with the learning tools, which includes the SmartWorks, is only 100. Yeah, $100. Okay. Are y'all getting any kind of assistance?
No.
No. Okay. And probably not through, because you're both transients. Okay. Because I tell my students, if you're on assistance, then you probably have to go through the bookstore for it to work. Okay, so there's textbook information. Let me go back out. Oh, that's another interesting thing up there at the top. Let me click on another one. Here's homework problem sets. If you go to the top, nope, it's not there. Call that up. This should be the handout that I gave you on the problems. And you'll notice that they're a pair of numbers. This 1.1 and 1.41. The 1.1 is in the third edition, chapter 1, and it's correlated to 1.41 in the first edition. The reason I do that is I have a copy of the problem solutions that instructors can get for the version 1. So that correlates. If you work problem 1.1 and you need to find out how it was done, go to 1.41 in Brightspace. Let's see, that's going to be probably here under this first exam. I still have some things to do with this Brightspace. Where is it? Solutions, here we go. Chapter 1, nomenclature, solutions. Here we go. So this will give you the solutions, and no. Okay, obviously it needs some more work. Topics. No, I don't want that one. I want this one. Here we go. Chapter 1 solutions there. Okay, as soon as it loads up. So there, 1.1, no, 1.41. Let's go down. Go way down. Close. There it is, 1.41. So that gives you a solution to that problem, because when they made the third edition, they had a correlation for second to third, but they didn't have one from 1 to 3, so I had to do that manually. Now I do have solutions for the third edition, but it's in a Kindle, and it's copy protected, right? So I can't extract the information. I am going to be able to get, let's see. When you get down to the inner chapter, inner chapters, there's no correlation between the inner chapter and previous problems. So they're all by themselves. These are third edition. So what I'm going to do is, I think I've got a way, I can take small clips out of my Kindle, and I can give you the solutions for those. Of course, that's if you go this route. If you go the homework route in SmartWorks, then you don't need that. That much you just make useless. I've had a couple of students in the past that put everything I give them, they work every problem. Actually, the more problems you work, the better you get at it. Your best, I tell my chemistry students, any class, I say your two best friends are curiosity. You always want to know more, and boredom. If you get bored working these problems, then you probably know them pretty well. Okay, so let me go back here. Come on. Oh, there's what I was, along the top, the breadcrumbs. Not every page has them, but if it does have them, then you can go back to, you can back up quickly to where you want to be using the breadcrumbs. Are you connected?
Yes.
Okay.
Yeah, I'm good with these notes on this, so I can take notes on top of.
Oh, okay. All right. There's another connection for Zoom meetings. You can get to the Zoom meetings there also. Websites, right? If you want somebody else's explanation for something, then my first choice is Khan Academy. Saul Khan is excellent. In fact, he does most of their videos, I think. And then there's these others down here, but you can take them or leave them. Okay, then each one of the exams is materials in a module. Right, so there's chapter 1, and this should be PowerPoints. I give you PowerPoints in 3 flavors. There's the PowerPoint slide set. So if you have Microsoft Office, you can open them up. They'll probably open up now with newer versions of Windows and whatever your browser is. You might be able to look at these in the browser. But just in case, I got the converted to HTML5. So the HTML file will load up in any browser. And then the PDF files, if you just want to see the sequence of slides. It shouldn't be a problem with this course because I don't have any, there might be some animations in there that PDF won't convert. But my other courses, I usually have videos scattered around, right, to help explain things. And when you do the PDF, those videos go away. But the HTML5 embeds them. So, all right, that's, let's see. And that was chapter 1. This is interchapter A, which is our first chapter in nomenclature, how to name compounds, how to write the compounds, how to name them, how to draw their structures. We're going to get a little bit of the structures in the chapter 1. But the interchapter A, we start off with very simple organic compounds. And then chapter 2, of course, whatever it has to do. I have interchapter B. I shouldn't have B in there. No, I need to move that. Interchapter B needs to be in exam 2. So I've got some fixing to do. So if there's any doubt, go by the syllabus and the schedule that on page 6. Right. That's what I follow. And I try to make everything else jive with that. In fact, before I do any of this stuff, I create the syllabus, get everything in there that's supposed to be and how I want the course structured. And then everything else follows from that. Okay. So let's see. And I don't know, we don't have a comprehensive final. We just have 4 exams and some quizzes. Like, let's see. Next week, we'll have a quiz on interchapter A, which is the first chapter on nomenclature. So I'll have maybe 10 or less questions to see if you're absorbing any of the naming. Organic chemistry is, chemistry itself is a language unto itself. And organic is even worse. Yeah. Organic, if you hear organic chemists talking to each other, then it's like a foreign language. It's gibberish. But they understand exactly what they're saying to each other. So that's the purpose of these quizzes, at least the first couple. Yeah. The third quiz is going to be on arrow pushing. And we'll talk about that later. But you have reactions and you're drawing arrows to where the electrons are moving. Okay. All this other stuff is required. I put that in there because I used the school template. So you can stop me anytime for questions too.
So, are interchapters just, kind of little sub chapters of chapter 1?
No, they're whole chapters to themselves. They're just slid in between the main chapters to help you focus on a particular topic. They're not that long usually. And they at least the first couple, in fact, A, B, and D are all about nomenclature. C is an inner chapter on molecular orbital theory and chemical reactions. So that's a little bit different. So I should ask you this question at the very beginning. Both of you have had general chemistry series, correct? Okay, good. Because for transients, I can't tell from looking at your profile in our system. I can't tell if you've had the prerequisites. We just if you're signed on from another college, then they just assume that you have the necessary prerequisites, and that would be a disaster if you didn't have them. Although there are some instructors in the country who believe in organic first. So their program, they teach organic first. I don't know how they do it, because I mean, there's so much you need as background to get into organic, but I'm sure they found some way around it. Otherwise, their school couldn't be accredited. Okay, so that's the Brightspace course. Let's stop that share and get back to our first chapter. Is this it?
I have one question.
Yeah, sure. Mhm.
Before our lecture on Wednesday, do you want us to have our ebook ready to go with our homework and everything?
Sooner's better.
So-
Yeah, because we're moving along at a pretty rapid clip. Most of the students that take organic in the summer, at least at this school, fall into two categories. You guys are different. Either they're in a program where they absolutely have to have both semesters of organic to progress in the next regular semester at their school, or they did poorly at their school. And community colleges have a reputation for being a little bit easier. I suffered through organic as an undergraduate, and I sympathize. What I want to do is try to make it as understandable as possible. And actually, what we want out of this course is to develop some understanding and some tools that can help you elsewhere. That's all the chemistry I ever took. That was my goal. So I'm not a chemistry, a bachelor's, master's, or PhD. But I took chemistry along the way because I knew it would help me understand my other topics and other subjects. So that's one of the goals I want to do is make that useful to you. There we go. Now we got the slideshow. As long as it's not chopping things off where they need to be. All right. So, got an idea of what organic chemistry is? Well, I can tell you what it isn't. It isn't inorganic chemistry.
Good.
But historically speaking, and this comes out of maybe the 18th century, 1700s, there was a concept called vitalism. And it was believed that, and this is when modern science was starting to get rolling, right? It came out of the middle 17th century. But by the 18th century, there were numerous theories, belief systems that were being discarded because they didn't fit the data. And one of those was vitalism. And the belief was that organic materials, were derived from living systems only. You couldn't get them any other way. And it required a vital component, which is another way of saying you need a living system. Well, let's see. I looked it up not long ago. See, I hadn't had time to modify my slides. So I need my crib notes. I'll start with Berzelius. You heard of Berzelius? Right. He was one of the scientists that proposed our current system of symbols for the elements, with a capital letter, and then if you need another letter, a small letter. It's a good thing that he won, because some of those other proposals were harebrained. Anyway, Berzelius was a doctor. He was trained as a doctor in Sweden, Uppsala University, I think. And in 1806, he proposed the name organic chemistry to encompass all those chemicals and compounds and reactions that occur in living systems, right? They still believed in vitalism there at that time. And then along came, let's see, here we go. Then along came a German, Friedrich Wöhler. What Wöhler did, Wöhler was trying to make a compound using ammonium cyanate. And he was trying to, let's see, he was trying to make ammonium cyanate from silver or lead cyanate and ammonium nitrate. And he ended up with a compound that wasn't what he expected. So when he identified it, he found out it was urea. And urea is supposed to be a biological compound. It comes only from living cells. So that was the first instance of an organic substance coming from a non-living system. So that sort of threw a wrench in the gears. We had to go back and say, all right, this vitalism idea is not working. So I also tell my general chemistry students, I don't know if you've ever heard this, if you have a theory that guides your understanding of any subject, we'll stick to chemistry. And theories are used to predict results. So if your theory predicts the wrong results, what do? Right, you have three options. You can tweak it, right? Modify your theory so that it'll give you the right answer. Or you can restrict its use. You can say, these are the boundaries. Anything outside those boundaries doesn't work. Right? And we do that with classical physics, Newtonian physics. Right? If the objects get too big, like black holes, we have to go to relativity. And if they get too small, then we go to quantum mechanics. Right? But classical physics works in this region. So that's the second option you have. The third option is throw it out. Just get rid of it. Right? It's no good. Start over. And that's what they did with vitalism. They eventually said, this isn't worth keeping, get rid of it. There are a whole bunch of those that came out of the Middle Ages that modern science discarded. Okay, so what is an organic chemical? Well, we've sort of over the centuries found out that organic chemicals, those that have these properties that were once assigned to vitalism, these chemicals had two elements in them. They had carbon and they had hydrogen in some connected way. And then there are others, like you put oxygen, nitrogen, sulfur. You can add those in, but they have to have carbon and hydrogen. So an example of a carbon compound that's not organic, carbon dioxide. It's the product of combustion of organic compounds, but it's not organic by this definition. So why are we so focused on carbon? Well, the nice thing about carbon is where it's located in the periodic table. Right? Right here. Right? It's not as small as hydrogen or helium, but it's in the second period, and that makes it a small atom. So you can pack a lot of them together and arrange them in different ways. But the reason you can arrange them that way is because carbon can form 4 bonds for each atom, covalent bonds. Now, you can make ionic compounds with carbon too, but we're focused on covalents. So typically, you will either have 4 bonds with the carbon, covalent bonds with the carbon, or if one of the bonds is missing, then that carbon in the molecule will have a charge. It'll either be a negative or a positive. We'll talk about those later. Carbon can be linked together in long chains. It can be polymerized. You make huge molecules. DNA comes to mind, right? Or some of the plastics we produce. Polyethylene is one commonly used. PETE, polyethylene terephthalate, is the one that's used for, I have an example here. Maybe this is, let's see. Yeah, this is PETE. Same plastic they use for soda bottles. Is carbon compound. And there are hundreds of thousands of compounds that have been created with this carbon backbone. And there are more being created every year in the pharmaceutical industry, in the synthetic organic chemistry industry. I used to live in Baton Rouge, and just up the road was Exxon, right? And they got shipments of oil in, and they started working on it. They fractionated it first, and then they took the fractions and started making stuff with it. And the nice thing about carbon is it can be single bonds. You can have double bonds between carbons. You can have triple bonds between carbons. They can branch. And all of these changes change the physical behaviors of those compounds. Okay. So the question arose, I remember I was taking my bachelor's degree is in biology. And I was taking a course in cell physiology. So the question was posed to the class, say, well, silicon, is in the same group as carbon, why can't we make compounds out of silicon? Well, first thing, it's a bigger atom. And the second thing is, here's an example. If you take the analogous compound for C6H12O6, which is glucose, and stick a silicon in there instead, and then burn it in oxygen, combustion reaction, it'll produce the glucose will produce carbon dioxide and water, right? A gas and a liquid. The silicon analog will produce a solid, right? Silicon dioxide, sand, right? That's not going to work, right? If that's a byproduct in your body, how does your body get rid of it? It can't be. Now, science fiction makes use of it. I remember an old, you probably haven't seen any of the original Star Trek TV series. Okay. There was one series where they had this creature that would eat through rock. And its cell physiology was based upon silicon, not carbon. They were really taking liberties. Okay, So we're gonna, some of the things we're gonna do now are just refreshers, right? Of what comprises an atom, right? You have in the nucleus, according to Ernest Rutherford's work, you have protons and neutrons in the nucleus, unless you're hydrogen. And then the most common isotope of hydrogen has no neutrons. But most of them will have neutrons and protons in the nucleus, very dense center. And then the electrons will be out here somewhere. And the relative mass difference between the protons, neutrons, and electrons is that most of the mass is in the nucleus. So if some particle comes flying through, it's the probability is that it's going to miss the atom. It's going to miss the nucleus completely because it's so small. So there's a relationship of, remember when you write a symbol for an element, right? There are four positions around that element for information. Remember that, right? That's the number of protons, the atomic number. This is the mass number, the sum of protons and neutrons. This is the charge, if there is one. And this is the number of atoms. That's what those positions are reserved for. So how do we make an ion? Remember that? You can't change the protons, the positive charges. Otherwise, you get a different element. So you have to get an ion from either adding or subtracting electrons. So if you add electrons to a neutral atom, you get a negative ion. If you subtract electrons from a neutral atom, you get a positive ion, a cation. Okay. All right. So we're focused on carbon. So let's look at carbon. So how would we write carbon? There's carbon. How many protons and electrons? Well, if it's neutral, we have, let's see, what is it, 6 or 8? 6? Be sure. Yes. Okay. So we have 6 protons. That means we would have 6 electrons in the neutral atom. And we have 6 neutrons, which means the most common isotope of carbon is carbon-12. In fact, that's the basis for all the others, right? Carbon-12 is given a mass number of 12.000 infinite. And then everything else is related to that. Okay, now the question is, how many protons, electrons does this cation have if the charge is +1? Well, it still has 6 protons, has to. But it has only 5 electrons. Okay. This is Joel Carty's idea of problem solving. It says think, solve. That's a little too simplified for me. Okay. Did your chemistry class, the general chemistry class you have, did it introduce the quantum numbers? Okay, good. Okay, so the principal quantum number is the first one. Right. And that can be anything from 1, 2, 3 on up. Okay. And the principal quantum essentially talks about the energy of that at that level in the electron region and its size. So the bigger the number, the bigger the orbital. Okay. So let's see. All right, we're getting a bunch of information here at once. The next one is what? L, right? And that's equal to n-1 up to, let's see, it can start from 0. It can go from 0, 1, 2, 3. And these, remember, they're branched. So each one of these can have a separate one of those. And then each one of these can go to This one. Now, this one, the L is shape of the orbital. It can be spherical, it can be have lobes on it, it can have donuts, that's type of thing. And we give these L's letters so that when we write the electronic configuration, we don't get all jumbled up with numbers. Right. Remember, this one's S, P, D, F. It can keep going on out, but you don't need them, right? Because periodic table ends at a full F orbital. Actually, the actinides end at a full F orbital, and then you go back up and finish off the D's in the, but you only need to go to F, right? And then each one of these can be minus L up to plus L. And then, of course, you have the spin. They can be plus 1/2 or minus 1/2. And that, all those numbers together would give you the electronic configuration of your atom. Now, if we're looking at carbon, right, if we go carbon like that, then the neutral carbon would be what? A full S orbital with 2 electrons. And then you go to the next one. That can be full. And then this one would have the other 2. So that's all 6 electrons for a neutral carbon atom. Right? So which are the valence electrons? Those right there. The highest principal quantum number gives you the valence electrons. Now, I think Carty focuses on the peaks. But you really can't do that because of the requirements for hybridization. Because if you try to make a symmetrical compound out of, say, methane, that's going to be a tetrahedral shape. Okay. With like that. And then we have carbon here, and we have a hydrogen there, and we have a hydrogen in the back, and a hydrogen here, and hydrogen here. So you get a tetrahedron. Well, you can't do that with 2 S's and 2 P's. Remember, you have to hybridize them. So you have sp3, you have 4 sp3 hybrid orbitals that give you that shape. So that's why I think that the valence electrons should incorporate all of those. Okay. That's one of the reasons I have PowerPoint slides is to keep me from wandering too much. Okay, so we can write electron configurations for any element in the periodic table. And some of them, well, all of them have valence electrons and core electrons. If you ionize an atom, particularly those that are in the second and third periods, because they're well behaved. When you ionize them, it takes a certain amount of energy to remove 1 electron and make a +1 ion. Then it takes more, about double the energy, to go to +2. That's as long as the electrons are from the valence shell. If you get down into the core, then those core electrons, they take 10 times as much energy. Okay. Now, we don't have time to go rehash the explanation for that, but it's just a fact. When we talk about ground state, what we're saying is that the most stable form of the element under those conditions. So at 1 atmosphere pressure and room temperature, the ground state for most elements are the ones that you're going to draw from the periodic table. Now, you could have a ground state with higher electron orbitals if you are, say, on Venus, right, where it's hot enough to melt lead on the surface. Then the ground state would be higher. That's the most stable. But for our purposes, we're saying ground state is the most stable, lowest energy. And in fact, that's what atoms and compounds are tending toward, the lowest possible energy state that they can attain. That's what drives the reactions. Okay, remember the Pauli exclusion principle? It simply says that no two electrons in any atom can have the same set of 4 quantum numbers. Right. So, and the Aufbau principle is how you build an atom. In other words, when you start going through the sequence, right? Hydrogen, helium, lithium, beryllium, boron, carbon, when you start adding protons and electrons to build the next atom, the electrons go into the next available lowest energy shell. That's the Aufbau principle. Hund's rule simply says that when you have a degenerate orbital, and degenerate doesn't mean like weird. It means that same energy state. So the p orbitals, the s orbitals only have one possible subshell. So that's why you can have an up and a down there with the spin. But the p orbitals have 3 subshells. Right? And Hund's rule says that depending on how many electrons you have to put in there, you got to put at least 1 in each of the degenerate orbitals before you can go back and pair them up. Right? In this case, you only need 2. So there's no pairing there anyway. All right. This is just review. I don't know. How long has it been since you took chemistry? Last semester? Okay.
This kind of stuff we covered in 115 now, which we did have together. So it's been kind of a minute since I've seen this, but I remember once I got this concept, it made a lot more sense.
Oh, okay. Yeah.
So I definitely need to review some of this, but
Okay.
it's there for sure. Yeah.
And the nice thing about understanding the way the atoms are built up is the periodic table makes a whole lot more sense the way it's arranged. Yeah. Okay, so when you have a covalent bond, the electrons are shared between the atoms. They have to be shared because the electronegativities of the individual atoms that are in the bonding are not high enough to completely remove the electron from its neighbor and make true ions, in which case the attraction then would be purely electrostatic. So they have to share electrons. And the example here given is the hydrogen gas, diatomic element, right? At a certain distance, you have the lowest possible energy. At that bond length and that bond energy, you bring those hydrogen atoms together, and if you try to push them any closer, they resist. Because at this distance, that sharing of electrons is ideal for the repulsive effects of electrons on each other and the repulsive effects of the protons in the nuclei on each other. Try to push them any closer, then you start getting those repulsive effects skyrocketing. That's why it takes a whole lot of energy and very dense atomic, very, very dense plasma and high temperatures in order to get nuclei to fuse. So when you want to fuse 2 hydrogens together, making helium, and give yourself a whole lot of energy, then you got to overcome that repulsive effect. And this graph only shows you part of that, where you're going from here and up there. Right? If you just kept going, as you get closer and closer, it just skyrockets. So it takes a lot of energy to overcome that repulsive effect to get the nuclei close enough so that now it's not the electrostatic repulsion that's giving you problems. Now you have access to the strong nuclear force, and that binds them together. So that's where fusion goes. But that's physics. We're talking chemistry here. So the covalent bond is under the localized electron model, you're overlapping atomic orbitals. Right? Each of the electrons are still belong to the atoms. They're just sharing them through their overlapping orbitals. But we find out that has its limits. That understanding has its limits when we talk about chemical reactions. Then to get a better understanding, in fact, be able to calculate the energies that are involved, we need another theory, and that's where a molecular orbital theory comes in. Okay, so this is an idea of what the spring analogy. The minimum energy is when the spring is at rest. That's your bond. All right, I think what Dr. Carty is getting at here is trying to direct your attention toward stability as a driver for organic chemistry reactions. How do you get stability? One of the ways is you spread the charge over a larger volume. Charge density at its minimum amount is ideal. So if you have two reactants in which the charge density is relatively high, and they get together and produce products where the charge density is spread over a larger area or even neutral, then you have a stability factor that's helping to drive that reaction toward products. Okay, so remember the notations for bonding. If you have one line, how many electrons is that? 2, right. So a single bond is one line. That's 4 electrons. That's 6 electrons between the atoms. And you can do that with carbon. Right? You can have carbon like that. You can have carbon like that. You can have carbon like that. In fact, we put hydrogens on the other side, right? 4 bonds, 1, 2, 3, 4, and put a hydrogen on this side, 1, 2, 3, 4. You got acetylene. Right? Every welder knows that one. They may not know why it works, but they know what it is. So these are bond energies for single bonds. Between hydrogen is 436. This is probably kilojoules per mole. Values are given in kilojoules. Well, of course, read this. Read the slide, Dave. So, and they're always given in as positive numbers. The reason they're given as positive numbers is the way we measure bond energy. We measure bond energy by adding energy to the bond to break it. How much energy does it take to break? And remember, when you talk about systems versus surroundings, did you have that discussion? Okay. Right. The convention is if you're adding something to the system, it's a positive value, whether it's heat or work, right? If we're talking about internal energy, it's either got to be heat and or work changes the internal energy. So if we add heat, not a G, Q, it's going to be positive. So we're breaking the bond, we're adding energy to it, so they're all positive values. That's why they're all positive values. And there's some that are stronger bonds than others. Let's see. Oxygen and hydrogen is higher. Ooh, fluorine and hydrogen is very high. Let's see. Silicon and fluorine is even higher. Is that the highest one we got in there? It might be. I'm just doing a quick scan. Oop, there's another one. What's that one? I can't see it.
Does that have something to do with the electronegativity?
Yes. But it's still, the electronegativity difference is not enough to create an ionic bond. It creates a very polar covalent bond. Right? It's because we don't have any metals and nonmetals in here. These are all, well, silicon is right on the break line, isn't it?
Yeah.
Yeah. So it could be considered a metalloid. Under these conditions, we would consider it a non-metal. Okay. And then if those were just single bonds. If we look at multiple bonds, there we have a carbon-carbon single bond is 339. But if the double bond is 619. Notice that it's more, it's a lot more, but it's not double the single bond. Right? Double the single bond would be 678. So, and if you think back to your discussion of how double bonds are formed by sideways overlap of the p orbitals, right? Those are not as efficient as on-axis overlap. So that doesn't add double the strength. It adds a lot, but not double the strength. And then triple bonds are not triple the single. And notice also that as the number of bonds between two atoms increase, the length, the bond distance shrinks. All right. So remember how to draw Lewis structures? I think they're kind of fun, actually. G and Lewis was onto something there. Except when you get into atoms that have access to d orbitals, then you can exceed the octet. Or in some cases, like beryllium and boron, in those compounds, you can have a deficient octet. But for our purposes, where we're bonding carbons to carbons, carbons to oxygens and nitrogens, the octet rule works great.
I mean, what word?
Most of the time, yeah. I hesitate to say always because there's bound to be one exception.
One that we worked with some that could see help.
Had what?
We had one exam where it might have been like one of our last exams, but we were getting into these Lewis structures, but then we were looking at the ones that could exceed the octet, and that was where I started to get confused. I was pretty good with
okay.
Yeah.
Yeah, some of my favorites are the forced compounds with noble gases, like xenon hexafluoride, which would be an octahedral shape. Okay. So hydrogen, single bond, 2 electrons. Methane, 4 hydrogens, each one, single bond. But when you get to now, we're drifting a little bit from organic by going to carbon dioxide and ammonia, but we're trying to make a point with Lewis dot structures. Carbons tend to make 4 bonds of some kind. Oxygens tend to make 2 bonds of some kind. Now, this is not a hard and fast rule. In other words, it's a starting point. Nitrogen tends to make 3 bonds. So that can shorten the solution to a problem, usually, if you start in that place. So we have each of these oxygens forms 2 covalent bonds with the carbon, and the nitrogen forms 3 covalent bonds, 1 each for each hydrogen. And you also have bonding electrons and non-bonding electrons, shared versus unshared. Right? Oxygen has those. In other words, if you look at if you draw oxygen, and it's got what, 8 electrons? Is it 8?
Yes.
Okay, 8. So that means when we draw the Lewis structure, we're only looking at the valence electrons. So right, so 1s2, that's out. We're into 2s2, 2p4. Right, so it has like that, like that, like that, like that. So it makes it's got this carbon over here, right, with just 4 valence electrons. So it's going to form a single bond with those, single bond with that. So we put an oxygen on this side. And then it forms a single bond with this one, a single bond with that. So that's where your double bonds come from. And you still have these lone pairs of electrons. And that contributes to its molecular geometry and its the words just flew out of my head. Yep. I have to wait for it to come back. So you remember how to draw Lewis structures. Okay, we won't have to dwell on that one then. Oh, we got an example. Maybe we ought to do one. Let's see how we do. We've been at it for almost an hour. We'll find a convenient stopping place. Do you need a break? Are you good now? Okay. HCO2 minus. HCO2 minus. So we take the valence electrons, right? There's 1 there, 4 there, there's 6 there times 2, right? Plus 1. That's we have 5 and 12 is 17 and 1 is 18. We have 18 valence electrons, right? Then you have to decide which one's in the middle. Well, if carbon's involved, it's going to be in the middle. Right? So we got a hydrogen here. We have 2 oxygens, 1 there, 1 there. So that's 2, 4, 6. That's 12 electrons we have to get rid of. Now you work from the outside and work in, right? Hydrogen's got all it can handle. So we got 12 electrons, 2, 4, 6, 8, 10, 12. Okay, so we got to make an octet for this carbon. It's only got 6 right now. So we'll take these 2 and make a double bond. That's one possibility. And then, of course, it's not complete unless we include the charge.
Where are we getting the -6 again?
2, 4, 6.
Oh, okay.
Yeah, you make single bonds first to get everybody connected together. And then you subtract those from the total, and then you place the rest of them. And then you follow.
We'll review some of the.
Okay.
Yeah.
Okay, but we could just as easily have taken 2 from here and made a double bond there, right? It could have been like this. Like that. So who's to say? They're both valid Lewis dot structures, right? So that's where Linus Pauling came out and says, well, I got an answer. Let's just resonate them. They go backwards and forwards, right? And sometimes we write it like this. Except when you do it like that, who's got the electrons? So the Lewis structures and the VSEPR model has its limitations. Oh, if I erase these things too soon before you stop me. All right, so there you go. There's your resonance structures. Now, resonance can be useful in organic chemistry when you start looking at reactions, because you may resonate between 2 forms. Actually, resonance, that's not strictly speaking true. When we talk about organic chemicals and the way they move back and forth on their own between this structure and that structure, it makes some of the atoms, when it moves to one structure before it moves back, that makes one of the atoms reactive. And that's where we can talk about That's why the product is a certain stereochemistry, certain shape. Because it didn't originate from this structure, it moved back and forth between this one and that one. And then while it was over here, bam, it reacted. I guess you could call that resonance. Okay, there's an incomplete boron trihydride. Now, when you have incomplete or exceeds octets, we're dealing with chemicals that really do exist. They have been identified. We know their formulas. What we have to do is explain. Right? I tell my students, nature just does what it does. It's our job to explain. So that boron trihydride is lacking an octet. We've used up all the electrons for BH3, but boron only has 6 electrons around it, not an octet. Well, you also get that with this possibility. That would be if it lost a hydrogen to something else, and the hydrogen took 2 electrons with it. That would make, this is called a carbocation. And that's not the only kind. You can have, anywhere you can have positive charge on that carbon is a carbocation. And those are reactive sites. We'll go into more detail later. You can have an exceeds octet too, like this. Let's see, paint myself into a corner. Can I name that? Well, my mind's not working. But you can exceed octets when the central atom has access to d orbitals, which sulfur does. Let's see. Okay. This is where I was headed with that earlier description. Hydrogen, only 1 bond. No lone pairs. Carbon can have 4 bonds with no lone pairs. If you get lone pairs, then you're into a different category. Nitrogen typically has 3 bonds with 1 lone pair. And we see examples there. The first one, the first one is ammonia. If hydrogen is here. Of course, you can put anything there as long as it's single bonded. And you can have a double bond with nitrogen, but it always has that 1 lone pair. Oxygen usually has 2 bonds with 2 lone pairs. The halogens, fluorine, chlorine, bromine, and iodine, they usually form a single bond with 3 lone pairs because they've got 7 valence electrons and they only have to use 1 of them to make a bond with something. And that gives them an octet. And then, of course, the noble gases, typically, well, neon, that's why they're focusing on neon, has no bonds and 4 lone pairs. Now, if you go up, neon, next one's argon, right? Argon's a little iffy. Next one is xenon.
Krypton.
Krypton. Yeah, krypton and then xenon. Those 2 have been forced into compounds, usually with the halogens. So I think that's why this chart focuses on neon.
Which ones can exceed the octet again?
The ones that have access to d orbitals. So if you're looking at principal quantum number 2, right? There's no access to d orbitals. It's just S and P. But 3s, you have 3s, 3p, and 3d are available. Right, 0, 1, and 2. So when you're going across here, you're only using s orbitals. Across here, you're only using p orbitals. But the d orbitals are still there. They just don't have electrons. Right, so when you get to sulfur and you bond sulfur with something and it exceeds the octet, then it has the ability to go to 3ds for to house those electrons. Now, when you get down to the fours, right, you go 4s1, 4s2, and then go to 3ds. Then you start building atoms with the Ds, right? All of these are Ds. Right? You have 10 electrons in d orbitals because there are 5 subshells, not subshells, with 2 electrons each. Yeah, anything, these guys right here or below, they can use d orbitals and see the octet. All right. That was the word, polarity. When you've got that, let's see, let me back up and say, what was I trying to talk about? The more polar, you asked me about a bond. I can't remember what it is now. Oh, was it, well, that'll teach me to forget. So you know how to determine whether a compound is polar or nonpolar, right? What 2 things do you need to determine the polarity of a compound? You need polar bonds. You need polar bonds, or actually lone pairs, but polar bonds for sure. Symmetrical, right? You need the geometry. You need polar bonds and geometry to answer that question. If you have all polar bonds, but they're uniformly spaced in a regular geometric shape, they cancel each other out. And overall, the molecule is nonpolar. But I've often wondered about this, and I think we're going to get into it in organic chemistry. If the molecule is nonpolar, but it has polar bonds, it still has regions of electron density that exceed the average. And those regions, whether they're excess electron density or they've come from a place which causes a deficit of electron density, then those become reactive sites. So even in nonpolar overall molecules, you can have reactive sites. And actually, there are 2 things, 2 concepts that will help you the most in organic chemistry. One is electron positioning. Where are the electrons? So how do they move? And the other is steric effects. Right? If you have a reactive site in a molecule, but you've got these big ligands sticking off here, and the reactant can't get to it, that's a steric hindrance. Okay, we'll look at that in a little more detail later. So you have these covalent bonds. You can have a nonpolar bond. The ideal nonpolar bond is where both of the atoms are exactly the same element. Right? For instance, nitrogen. That's the same stuff we breathe, nitrogen gas. That is perfectly nonpolar, right? Because each atom has the same electronegativity. Nobody wins. But you can also have covalent bonds where the bond is polar. And probably one of the most polar, not the most, but one of the most polar covalent bonds is hydrogen fluoride. As the gas, not dissolved in water as the acid, but as a gas. That bond is very polar, like that direction. Okay, remember those arrows? So this would be slightly negative, and this would be slightly positive. And then remember the, I think it was Linus Pauling, Pauling's electronegativity chart. Right, you take the periodic table and you assign numbers, and the largest electronegativity is in the upper right-hand corner with fluorine, 4.0.
It's super tiny.
Yeah, oh, size too. Yes, electronegativity, right, from lower left to upper right, and electronegativity increases. So cesium is about the least electronegative, which means, yeah, way down in the lower left-hand corner. And it's going to, that means that it's very easy to remove that valence electron. Okay. So far we just, oh, there it is. Now this one says 3.98. Okay. Well, these values didn't just materialize out of thin air, right? They are calculated based on a formula that Pauling proposed. Let's see. And in order to tell whether the bond between two atoms is polar covalent, non-polar covalent, or even ionic, is you subtract the smaller one from the larger one and see what that number is, where it fits.
What are the rules for that again? Like if it's greater than 1 or?
I think it's 1.2. Right. Less than 1.2 is non-polar covalent. Greater than 1.2, if they're both nonmetals, is polar covalent. If there's metal non-metal, then that's ionic.
Wait, you say, can you write those down?
Let me see if I've got a slide.
And I'm sure I have them somewhere in my notes.
No, they don't have them here. I'm working from memory here. I think it's 1.2. 0 to 1.2 is non-polar bond, covalent bond. Then 1.2 to 1.6, I think, is polar covalent. And 1.6 to whatever is ionic. Let's see if that works. Let's take lithium. It's about 1 subtracted from fluorine, which is about 4. So that's 1 from 4 is 3. Yeah, so that's ionic. How about, let's get them a little closer together. How about aluminum and sulfur? So that would be 0. Let's see, 1.61 and 2.58. .97. That's still ionic. Let's get them a little closer. How about nitrogen and oxygen? Right, that's 0.4, 0.4 right here. Nitrogen and oxygen, 0.4. So that'd be non-polar covalent. The closer they are to each other, the less the polarity, if any. You'll have to check, you'll have to look that up. Yeah. I don't think they're in the organic book. I think they're in my general chemistry book.
I have them somewhere back in my notes too, but.
Yeah. This is where I'm kind of iffy right here.
Okay.
If I had my general chemistry slides, that I've got them there on the slide, so I don't have to rely on my feeble memory. Okay. So we're talking about dipoles. When you have a covalent bond and the bond is polar, then we have what we call a dipole. And that affects the physical behavior of a compound and the chemical behavior. Physical behavior, for instance, water. Water has a very large dipole. Right? The bonds are polar. Right? And with these lone pairs up here, we have an extremely polar molecule. That's why water will dissolve. Well, they call it the universal solvent. That's not exactly true, but it's close enough. It's a universal solvent for all ionic and polar compounds because of this polarity. Like dissolves like. There are some cases though, and you probably remember those from your general chemistry where those anions and cations get together and they just drop out of solution, right? They precipitate. So doesn't work for everything. The other thing that this does is it makes water a liquid at room temperature. If it followed the pattern of other hydrides in its group, right? Sulfur dihydride, selenium dihydride, if it followed that pattern, then its boiling point would be way down here in negatives Celsius, but it's not. And that's largely due to hydrogen bonding. Remember hydrogen bonding? So when you get this water molecule in here, you got another water molecule close to it with its negative charge form that bond. And that keeps it in the liquid phase at room temperature. There's not enough energy at room temperature to break that bond. So that affects its physical behavior. Then the chemical behavior also, since this is a polar molecule, the chemical behavior also allows it to dissociate or ionize one of those hydrogens, right? And that's where you get into acid-base chemistry. And for organic chemists, sometimes they want that, sometimes they don't. Because if you're pushing for a certain reaction to take place, but water is competing with it because it's able to do this stuff, then you want a non-aqueous solvent to conduct your reaction. So there are several things that go into finding the right solvent for your chemical reaction if you're doing this synthetic organic experiment. One is solubility. What will your reactants dissolve in? Will they dissolve in water? Well, okay, if they do that, then fine, except is water a potential reactant? If it is, you can't use it. So you need to find another polar solvent that will not contribute hydrogens. Okay, these are various dipoles, and this is illustrating the fact if you have just two atoms in there, of course, if you've got a polar bond, you've got a polar molecule. And then when you're looking at CH4, right, methane, then that's nonpolar. And nonpolarity, the more nonpolar, the lower its boiling point. So dinitrogen, right, we looked at that one earlier, is perfectly nonpolar. And its boiling point is minus 195 degrees C. So while we're on the topic, well, if it can form a liquid at temperatures below 195, why? It's nonpolar. What's holding them together? Remember that? It's those temporaries. The temporary distribution of electrons.
London dispersion. And so all of them have the London dispersion.
Yeah, everything has it.
And then what are the ones? This is another thing I had in my notes somewhere deep away in all of this. But what are the elements for the hydrogen bonding? I know it's hydrogen can bond with what?
If you have oxygen and hydrogen, nitrogen and hydrogen, and I think sulfur. No, not sulfur. That's not hydrogen bonding. Fluorine. Like fluorine, nitrogen, oxygen. I'm pretty sure.
What? I don't know how much we're going to be looking at all of this, but are we doing anything with the dipole one? There's London dispersion, dipole, and then the hydrogen bonding. Are those the only two? I mean, the only group?
Yeah, this is a special case of dipole. And then you can have dipole ionic. But that won't be,
We didn't look at that one very much.
well, that's like throwing table salt in water. What happens is process called hydration. Now that's a significant effect in organic reactions, this hydration. Work. Sort of. All right. So what's the most polar bond in this molecule? Draw a dipole along that bond to indicate direction in which the bond dipole points. Okay. We got carbon, carbon, oxygen, carbon, and hydrogens. And your lone pairs. And then hydrogens here, and then lithium. All right. Look at how far apart they are. These bonds are not going to be polar. If we go back and look at the hydrogen is 2.2 and carbon is 2.55. It says 0.35. It's nonpolar. These are all nonpolars. Those are going to be nonpolars. Carbon and oxygen are probably slightly polar. Let's see, that would be well, technically it's nonpolar. So this one right here is going to be polar toward carbon. Carbon is more electronegative than lithium by quite a bit. Right? It's about 1 subtracted from 255 is 1.55. So that would be a polar bond. There we go. That's the only one that gives us a difference in electronegativity large enough. Let's see. Now they're saying that's 1.57. Yeah, okay. But we did, oh, okay. Yeah, we're working from that table. And that gives us the polar, I suppose that's a covalent bond. Typically, though, metals and nonmetals form ionic bonds. 1.57, I think that might be ionic. Yeah, that's maybe the breaking point is 1.6. We're saying that that's covalent. Just barely. Okay. Most organic chemistry books like to use these electrostatic potential maps. The reds are the more negative, and the blues are the positives. And then the colors in between are more or less neutral. So if you look at carbon dioxide, you see that carbon dioxide is a linear molecule with polar bonds, which means that overall it's nonpolar. But it has regions of electron density, increased electron density around the oxygen atoms. So on a local level, you find that the carbon is deficient. I mean, it's not a full charge, but it's deficient in electrons, and oxygen is excessive in electron density. Let's see. Okay, you took both general chemistry courses, so you remember crystal structures, the unit cell. Did y'all go through that? Go over that? And closest packing model.
Is that like lattice structure?
Yeah.
But we did not do lattice structures.
Okay. So what we find is the most efficient way to pack sodium and chlorine together is in a cube. Right? And if you take table salt and spill it on, this would be great, on a black surface, and use a magnifying glass, you see a whole bunch of little cubes. So the arrangement of ions in a structure are dependent upon both the charges of the cations and anions, and their relative size. Let's see. I can't say that ionic bonding is not going to enter into organic chemistry discussions, but it's limited. And it has its uses. For instance, some reactions, organic reactions, take place in basic solutions, right? So you're going to add maybe sodium hydroxide to the solution to make it more basic. And that promotes a certain type of reaction. Whereas if you add an acid to it, then it would promote a different reaction, and those are ionic effects. Now, formal charge. Did you guys cover formal charge? Okay, good. Formal charge seems to be something, it's an animal particular to organic chemistry. And it makes sense because it's not really a charge. It's just a way of bookkeeping, a way of tracking the electrons. And one of the first ways that my students learn to use formal charge is to decide whether a Lewis dot structure is valid or not, or which one is preferable. Because you want the Lewis dot structure with the lowest accumulated formal charges of all of its atoms. So this one, CHO2, has, if we look at, say, the oxygen, we say oxygen in its unbonded state has 6 valence electrons. How many valence electrons does it have in this structure? Oops, I think it's only 1, isn't it? And then hydrogen. So this is going to have 2 lone pairs, and this is going to have 3 lone pairs. Yep. Okay, so if we look at this, it has 6 electrons in its unbonded valence state. Then how many does it have in here? Half of a bond, 1, 2, and then these belong to it all together, 4, 6. So its formal charge is 0. For this one, though, you've got 6 minus what? 2, 4, 6, 7. It's a minus 1 formal charge. How about the carbon? Carbon has 4 in its unbonded state. It has 1, 2, 3, 4. Minus 4, 0. And then hydrogen's a no-brainer.
How's the hydrogen have 4 again?
Hydrogen doesn't. Carbon does.
Oh, right.
Right. Hydrogen's only got 1, and it gets 1 from that bond equals 0 if you want to be complete. Right. It's the neutral atom valence electrons minus the electrons that are assigned to it in the bonded state. And it gets 1 for each line, for each bond. So it gets 1, 2, 3, 4, 5, 6. Subtracted from the valence. So these, there's a lot of this is learning language. And you probably have come across this one in your general chemistry, the localized versus delocalized electrons. Localized electrons are effectively attached to an individual atom. Delocalized are those electrons that are spread out over 2 or more atoms in the bonding system. Delocalization tends to stabilize a molecule. So if you had, let's see, comparison. If you had this ring structure, and when we draw organic compounds, wherever 2 lines meet is a carbon. Okay, so there's a carbon here. There's a carbon there, carbon, 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 carbon. If we And carbon has 4 bonds available to it, right? If we just leave it like that, then it has 1, 2, and these others that are never written are hydrogens. Right? So you got the complete structure written. If we put the carbons in here and the bonds and then the hydrogens, and we put everything in there, that's a complete structure. But it takes forever to write this. So we write it just like this. And it's understood that excuse me. Let's see, 1, 2, 3, 4. Cyclohexane. Because it has 6 carbons. Hex is 6. Remember your prefixes? Okay. Now, if we have a system with double bonds alternating like that, we have a much, much more stable system because these double bonds are above and below the plane of this molecule and they delocalize. So if you look edge on, or if we, sometimes we draw it like this to emphasize the fact that this is not a double single. Actually, we would be better doing it like this. Otherwise, we'd have to write resonance structures with a double bond shifted 1. This is benzene. And sometimes we write it like that to emphasize the fact that all these pi electrons, right, in the pi bonding system are delocalized over the whole molecule, and that stabilizes it. Benzene rings in any molecular structure are very stable. I mentioned earlier that chemistry is not my degree. My last degree was in agronomy, crops and soils. And one thing to learn is the progression of decay. Say a tree falls in the forest. What happens to it over time? Well, the microorganisms, actually the larger creatures like beetles and whatever, come in and chew it up. They reduce the particle size. And then you also get invasions of bacteria and fungi. And the first thing they go for are the easy to dislodge side groups. Right? Anything that's attached on the side of one of these rings, say, they'll chop those off. There's very easy. The enzyme systems available to do that for most cells, nearly all cells can do that. But once they get down, once they've reduced the structure of the wood to where you have, they've gotten rid of most of the cellulose too, because cellulose is just a string of glucose molecules. It's a polymer. And they're easy to break and digest. But when it gets down to these, which is part of the part of the tree called lignin, once it gets down to these, they're so stable, it takes very specialized fungi with special enzymes that are able to break those apart. They're the last to go because they are so stable. And this is delocalization of the electron density around a molecule. If you can spread the electrons out over the whole molecule, the more you can spread them, the more stable it becomes. Okay. We talked about resonance structures already. When you use this solid and dashed line business, then you can't put the electrons on the oxygens anymore because they're now embedded in those dashed lines. When you put electrons on an atom, you're saying these electrons belong to that atom. That's the localized electron model. So when you draw it like this at the bottom right, then you can't put electrons on it. So it's that actually signals the limits of this Lewis dot structure system. Let's see. Yeah. I don't know what he was thinking with that slide. So, a resonant structure, right? Okay, so here, yes, I was curious. Was I naming it correctly? Where a molecule resonates between two structures that don't look a lot alike. Right? We have this carbocation on the left, and it's an ether. Right? We haven't talked about that yet. Ethers are like oxygen in the middle and then two carbons on either side or whatever. And that, let me draw that so I can talk about it. I don't know if I'm taking too much time or not. Guess we're okay. Let's see. So we've got this carbon, hydrogen, got a methyl group. So the bond is between the carbons. And then we got the oxygen. And then we got another methyl group. Okay. So that, and this has to have a positive charge because it's only got 3 bonds to it. Right? Think of it as if another hydrogen was in here and the hydrogen left and took the electrons with it. Okay. What can happen is this positive charge can shift over to this oxygen. And if it does that, then these electrons have to move back to take that place. And when they do, they make a bond here. So we're putting the positive now on this one and making a bond with it. Now, the way to check yourself is to count up the electrons, right, in your bonding system. Right? 2, 4, 6, 8, 10, 12. This one lone pair. So we have 12 electrons in that system. And before we had 2, 4, 6, 8, 10. Let's see, where's the 12? 2, 4, 6, 8, 10. Did I count too many? 2, 4, 6, 8, 10. Oh, 2, 4, 6, 8, 10, 12. Yeah. I forgot to count that one. So we got 12 electrons in both systems, in the bonding and lone pairs.
Can you, I don't, maybe I just haven't seen it written with this little plus with the circle, but can you explain that again? Is there another way of writing that maybe I've seen? Or is that pretty?
That's pretty consistent. Yeah, that's pretty consistent. And it's particular to organic chemistry. Yeah. So I wouldn't expect you to have seen it before.
So all that's happening here is this. So I see that a double bond is being made.
With 2 electrons from here, makes a bond there.
Okay.
And if you let's look at the formal charge and see if that can explain it for us. Right? What's the formal charge on this carbon? 4 minus 2, 4. Let's see. 1, 2, 3, 4. Minus 4 equals 0. How about the other one where we have the plus up here? And we have these lone pairs down here. Right, so we have 4 and we have 1, 2, 3. There's your charge.
Right. That makes sense.
I don't know why they didn't put that in here. Oh, we did. He did. He did explain it that way. I just have to read it.
Oh.
Yeah. Well, since I didn't make the slides, I'm entitled to miss a few. If I teach this course again, I'll go in and modify the slides. All right. So what does this look like on an energy diagram? When you delocalize the electron density through resonance structures, if you have more than one possible arrangement of bonds and lone pair electrons in a molecule, then that system is said to resonate. And in fact, what happens is the electrons are spread out over more volume of the molecule. And that reduces the energy. The resonance hybrid is at a lower energy than the individual structures would be. Right? The reality is that lower energy situation is where the molecule really is. And this is where you're saying those contributing structures are located. They're not real. This is real. We know that because we can measure the length of these bonds. Right? If we measure the length of the bonds, this one should be shorter than that, right? Because it's a double bond. Double bonds are stronger and shorter. But it's not. When we measure those bond lengths, both of those bond lengths are exactly the same. So this is reality. And this is trying to explain it with a theory that has its limits. Okay. Oh, here's my benzene molecule, right? We can resonate between those two forms, right? See, the double bonds have shifted one carbon to the left or to the right, whichever the case may be. And it resonates there. But actually, the bond length of every carbon-carbon bond in that molecule is exactly the same. So that's why we know this is reality, and that's an attempted explanation.
So that's where you, would draw the circle in between rather than the dotted lines.
Yeah. And the circle is sort of, it talks about the, if I had a three-dimensional picture, there would be a donut of electron density above and below the plane of the benzene molecule. It's planar, right? All 6 atoms are in the same plane. And you would have electron density above and below for the pi system. Right? Those overlapping pi bonds, overlapping p orbitals. Remember, when you get a carbon, let's see, the carbon in the system that's the carbon in the system has, each one of these has a hydrogen with it. Carbon. Okay. So if we have, say, a double bond there, there, and there, and if we look at the geometry for each one of these carbons, that's 3 groups around it, and the VSEPR model says it's trigonal planar. So it's perfect. Like that. So there'd be 1 carbon here, 1 carbon there, 1 carbon there, and hydrogen there. Nope, excuse me, there'd be another carbon. Anyway, where was I going with this? Oh, this double bond, remember, if we've got on axis here, here, and here, what's the hybridization on that carbon? It has to be sp2. That means we've only used 2 of the p orbitals, and there's an unused p orbital on each carbon that sticks out like that. And those unused p orbitals overlap and give you the double bond. Well, actually, in this molecule, they give you a double bond, a bonding system where everybody's bonded and the electrons are delocalized over the entire molecule, both above and below the plane. So that unused p orbital is what goes into that system, that circle system, the donut. And that adds stability. The more delocalized you can make your electrons, the more stable the molecule. Okay. Okay. This is the same molecule we were looking at before, wasn't it? Except now the carbon has an octet. Yeah, carbon has an octet, 2, 4, 6, 8. If we look at the formal charges here, we find that this one is 4 minus 4 is 0. This one is 1, 2, 3, 4, 5, 6 minus 6. That's 0. Formal charge. That's a formal charge of 0. And this carbon has 4 around it. It's 0. Right? That's perfect. They're all zeros. If we move electrons around and say, make this into a single bond, right? Now it has an excess of 1 negative charge. So now it's a -1. Well, we move those electrons, let's see, 6 of them, excuse me. Move those electrons out of there, and then we moved and these 2 electrons in here to make a double bond. So that's 1, 2, 3, 4, 5. 6 minus 5 equals +1. And 6 minus 7 equals -1. That's an undesirable Lewis dot structure. I mean, the more favored one is the one where all of your formal charges are 0. Now, that doesn't mean that this one does not exist, even for a flash of a second, but it's not the most stable form. Okay. So when we're looking at resonance structures, the first rule is all the atoms have to stay in their relative positions. Right? You can't move atoms around. You can move electrons, but not atoms. And this is where we start to work on curved arrows. Right? We got some rules for using curved arrows. I've got a full discussion of that later. It comes in, actually, I saved it for exam 3 material because curved arrows are very useful when we're looking at proposed mechanisms for chemical reactions. But I guess this is as good a time as any to introduce the topic. So what has happened is, let's remove some of this extraneous stuff here. Let's put it back the way it was. The ideal situation, that. Okay. So if you're going to use curved arrows, you never start on an atom. The arrow starts with electrons, either lone pairs or bonding electrons. So we could start from here, or we could start from there, or there, or there. We never start on an atom. Now you can end up on an atom, or you can end up on a in a bond. So if we started here, we take these 2 electrons and we put them in there to make a bond, then these 2 electrons are going to move into a lone pair situation. And that's what gives you the extra pair here and the bond here. Right, there's a whole set of rules that go with curved arrow. Sometimes they call them curly arrows. And we're moving valence electrons only. Okay. Well, we got another example. If we look at this molecule with 3 carbons and 1 double bond, and one of the carbons is a carbocation. Now that is a valid resonance structure, where you go from, you move these 2 electrons in that bond and put them over here in that bond. And what that does is that changes this formal charge to 0, and it makes this formal charge positive.
What is a carbocation?
It's a carbon that's positively charged. Yeah. Sometimes I forget to define my terms.
I mean, it's right there in the name, but I didn't know if it had any extra.
Yeah, that's a good habit to get into. Look at the name. Something's got a name that usually means something. Like let's go back as simple as possible. Atom. What does atom mean? Atom comes from the Greek. Tomos means to cut or divide. And a in front of any word is the negative. So atom means not cut. You can't cut it anymore. That was the belief. Of course, we know now that you can, subatomic particles. But when Dalton proposed it, they thought that atoms were just jelly-filled bags. Anyway, back to the topic. Okay, so for the last one, we have I think that's formaldehyde. No, that's methanol. Methanol. Yeah. I think. No, that's the carbocation. Methanol would be CH3OH. If you take one of those hydrogens away, CH2OH, and that leaves the carbon with a +1 formal charge. But now, if you take 2 electrons, and if you have an option to move electrons, start with lone pairs, right? Because then they don't belong to any. I mean, they belong to that atom, but they're more free to move. Right? So we're going to take those 2 electrons from the oxygen and make a double bond out of them. And that makes the oxygen deficient in electron density with a +1 formal charge, and it neutralizes the carbon formal charge. Now, if you do these enough, you just say, all right, we're going to move this. Okay, this is what happens. Right? You just know it rather than having to sit down and calculate it. That's why practice is important. Let's see. There is formaldehyde, CH2O. That's formaldehyde. And if we move 2 electrons out of that double bond onto the oxygen, that makes the carbon deficient and the oxygen excess in formal charge. But it's highly unlikely. It does happen, right? But the preferred state is the left-hand structure. But what that also makes available is for even a microsecond, if it resonates back and forth and produces that excess formal charge on oxygen and deficient formal charge of carbocation, then those are reactive sites. And if you have something in the vicinity that is attracted to one of those sites, you'll get a reaction. Right? Even though the preferred state is on the left, if it's in the right-hand state for just a split second, that's all the time you need to get the reaction. So one structure is not always the most stable structure, is not always the best one. Although, if you can get a stable structure with a difference in formal charge, then the likelihood of that reaction proceeding is much greater. Okay, we've already talked about benzene. This system where you have a carbon chain, and notice that they're zigzagged. They're zigzagged because of the way, we need models. I got models in the other room. We're eventually going to need models. So in addition to buying the book, get yourself a model set and keep it at home. I've got models here we can build, especially when we get into stereochemistry, right, and isomers. Then you're going to have to build 3-dimensional structures so you can see how they look when you rotate them. But for now, whenever we write carbon in a chain, it's usually a zigzag of some kind. In this case, we've got alternating single bonds and double bonds. And hydrogens, right? So 1, 2, 3, we got to have a hydrogen on each one of these. So we know from VSEPR that 1, 2, 3 groups means that's trigonal planar around that carbon. Remember, 3 groups, trigonal planar. But one other thing that happens with the difference between single bonds and double bonds is the double bonds tend to lock the rest of the molecule in position. They don't rotate. Single bonds will they'll rotate all day long at blinding speeds. But when you have a double bond, it's locked in place. Now this is going to rotate, that's going to rotate, but this won't. Okay. All right. Let's see. Let me make something here. For our example there, they have a carboanion on the end. That, 2. Well, it would be consistent. There we go. Okay. So what can happen? Well, this one can go over here and make a double bond. Like that. Well, what happens to, oh, and also when it does that, you have an excess, let's see, carbon to carbon. Yeah, makes that double bond. Well, doesn't yet because I haven't erased those. But you get a cascade effect. So it moves on down the line. And you can go all the way down to the other end. This is called a conjugated system. So whenever you have a double bond and a single bond alternating in a string of carbons, that conjugated system allows for delocalization of the electrons throughout the molecule. And the longer the length of the molecule with those conjugated system, the more stable it is. And you can see that spectroscopically. In other words, with a short conjugated system, it may absorb light in the ultraviolet. But if you get it longer, it'll absorb light in the visible, and you can get colored compounds. So look at oranges, lobsters and crawfish. Their shells are red because they have this conjugated system in molecules called astaxanthin. And it's because the molecules are very long, they're conjugated, more stable, and they absorb energy in the visible range. Of course, they don't absorb red because that's the one you see.
So both of these ways are like the correct way to write them out, but it's just showing me all the possible structures.
Right.
Okay.
How the curved arrows can move electrons, and once you get established in, say, you go from the first one on the left produces this one. Now you have that lone pair moved onto that carbon. Now this carbon is negative instead of that carbon is negative. And then next one is this one's going to be negative, and then the last one's going to be negative. So it's like that negative charge is just marching down the molecule. And these are all valid structures. They're actually 1, 2, 4. Yeah. 4 valid structures resonating. Okay, now we're going to look at notation. How can we draw these things faster? We have to understand what we're writing and how we're writing it. The example here is propane. Right. We'll talk about those in the interchapter A, how these are named. This is propane. It has 3 carbons, and it's the same stuff that you grill your steak with, or heat your home, or cook your food in the house, heat your water. Propane. If we draw a valid Lewis dot structure, that's what it looks like. Right? It's a string of carbons, and the hydrogens fill in the rest. All single bonds. Okay. The point was shorthand notation. All right. So for propane, we would see it written this way, say in a sentence. Right. If we wanted to say something about the molecule and not just write propane, but actually put the molecule in there, we would write it in this shorthand notation. Now, this looks like one of those hydrogens is bound to that carbon and then bound to this carbon, but it can't happen because hydrogen can only have one bond. So what we've done is we put the CH3 here when actually it means this. And then the H3s are here, and the H2s are there, and the H3s are over here. That's shorthand notation. All right. Formal charges on atoms with various bonding scenarios. All right. This carboanion has a -1 charge if it has a lone pair on the carbon, but no bond. Right? If it had a bond, then those 2 electrons would be in a line connected to something. Right? It would be like this, connected to something. Then you would have 1, 2, 3, 4, -4 would be 0. But if we put these 2 lone pairs here, like that, then they both belong to that carbon. So carbon is 4, 1, 2, 3, 4, 5 equals -1. So that gives that carbon a minus charge because it has both of the electrons instead of just one of them. Let's see. If we have a positive charge, then that means both of these electrons are missing. That means 4 minus 3 equals +1. Okay. Nitrogen, actually, it's best to start with the uncharged, the 0 formal charge. If we look at ammonia with this lone pair and 3 bonds, right? 5, 1, 2, 3, 4, 5, -5 equals 0. So that's the if this is hydrogen, then it'd be ammonia. If not, it's just an amine. But if we take those 2 and make a bond, now nitrogen only has 1, right? Because it's only half the bond. 1, 2, 3, 4. So that makes it a +1. So if we put 4 bonds on that nitrogen, we get a +1 charge. And that the perfect example is ammonia, right? Formal charge of 0 going to ammonium. If we put 4 hydrogens around it, now it's a +1 charge. And you add nitrate on there and 6% fuel oil and a blasting cap, and you got yourself a nice bomb. If we go the other direction, right? If we go the other direction with nitrogen, see, this would be perfect. We go the other direction, and those lone pairs are missing. Now we have a +1 charge. Oh, excuse me. I'm going the wrong direction. If we take this one and let's see, lone pair, neutral, 0 formal charge. Now, if whatever this is connected to is gone and we leave behind those 2 electrons, now we have minus one formal charge. So I guess the lesson here is if you have the carbon, nitrogen, oxygen, or halogen bonded to something, the number of bonds they prefer, carbon is 4, nitrogen's 3, oxygen's 2, halogens are 1. Then if you add a bond, you get a cation, not a carbocation, cation. If you remove a bonded atom to it, then you get a negative. As long as those electrons from the bond stay behind. I think that's the whole point of this slide. Yeah, sure, we can take a break.
So to prepare for like the quizzes and tests, you suggest like doing the practice problems over and like in a book.
I wouldn't say it that way because that implies just memorizing the procedure for that one problem. Understand why the problem solves the way it does. That's the key. So that's why working several problems that are in the same genera, only with slight differences, can give you a better perspective than working the same problem over again. And that's why I think that SmartWorks is going to help because it gives you, I've got a bunch of problems in there, and probably at least half of them you're going to get wrong the first time, and then it gives you a hint, and you go back and try it again, and then things, after cycling it several times and finally getting the right answer, maybe the light bulb will come on. Yeah, the things that we remember, it's funny how the brain works. The things that you remember for the longest time are the ones that you struggled with. I know when I was taking organic chemistry as an undergrad, my best friend and I were in the same class, only he had taken it once before. And the second time around, he did better than I did because he'd been struggling with it for a while. Okay. All right. So when we take that structure, right, this 2-methylbutane, and we'll learn how to name those later, that 2-methylbutane, and we write it in the condensed form, in that linear text form, that's the condensed formula. Let's see. And it's similar to yeah, it's similar to inorganic chemistry when you have a group, say a polyatomic ion like sulfate, SO4, 2-, and you need 2 of them in that molecule. And you have to put a parentheses around it and a subscript of 2 because the polyatomic exists as a unit. You can do that in organic if you have, say, if we had CH3 with that parentheses around it, that's understood to be just one of them. I don't know why they put that parentheses in there. I don't think they need it. But if we needed 2 of them, then you would put a 2 under it. And that means that those 2 are chained together in that position. I actually, no, when you put, if I did, what's my marker? If we did that, CH3, CH, and say we had a molecule, not this molecule, but one that was like that. Let's see, 1, 2, 3, 4. Let's do it the way they do it. 1, 2, 3, 4. Okay, I see what's okay. I'm remembering now. when they put a parentheses in organic chemistry, when you put a parentheses around a CH3 group, that means this is branched off of that. It's not in a straight line. So if we have 2 here, that means this would have that carbon on this side. It would have, it wouldn't have that hydrogen either. It would have this on that side and this up there and this down here. That's what that would mean. When you use parentheses in organic chemistry, you're branching. Okay. What we learned is acetic acid, proper name is ethanoic acid because it's derived from ethane, 2 carbons. I still like acetic acid. Okay. Now when let's see. Yeah, we can condense it even further. Rather than using condensed structure in a line like that, we can write it structurally and leave out the carbons. Like I mentioned earlier, wherever 2 lines come together is a carbon. It's understood. If it's anything else, you have to write it in. So if one of these, say we had a sulfur bridge in here, we put a sulfur right there, we'd have to write that in. If you don't write it in, it's assumed to be a carbon. And if there are no charges on any of those carbons, then it's assumed also that if it's not bound to a carbon, it's bound to a hydrogen. Right, so we leave the carbon symbol out, we leave the hydrogen symbols out, except on the ends when they're bound to non-carbons. So the reason it zigzags, if you look at the 3-dimensional structure of, say, methane, you got this triangular base. Then you got another hydrogen up here with your carbon in the middle. And then the actual bonds are here, 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 here. The bond angles, remember what the bond angle is methane is? It's the only one that I have my class memorized. The rest you can deduce. This is 109.5 degrees bond angle. Okay. So if instead of a hydrogen here, we put a carbon, and if instead of a hydrogen there, we put a carbon. So there's your zigzag. And then these 2 other hydrogens come off at their angles. So that's why we draw the zigzag like that. Okay. That's the convention. We can also, once we've drawn this zigzag, we can add various side groups or functional groups. Functional groups, generally speaking, are those that modify the chemical behavior of the molecule. So we can branch the molecule, say add a methyl group. We can turn it into a cycle. Right? This is cyclohexane, and then it has an ethyl group. That's a carbon, which is why it's ethyl. And we'll go over the rules in a minute. But these functional groups, and they're not always carbons. You can have functional groups that are made of nitrogen, sulfur, the most common. And we'll go with NO2 as a functional group first, and then we'll get some others. Okay, when we talk about functional groups, these are the some of these are carbon-based functional groups. So if we have let's just go ahead and name them. If you have a string of single bonded carbons, this would be 1, 2, 3, 4 4 carbons. This is known as an alkane. All single bonds among the carbons. So you can go through a homologous series of alkanes. You can go ones where carbon's not bonded to anything except hydrogens. Then you can put 2 carbons in here. Then you can put 3 carbons in here. Let's see, 8, 4, 5, 6, 7. I'll go down to 8. So we have 10, we have 22, we have 14. That's wrong. 12, 16, and 18. This is a series, a homologous series of alkanes. They're all single bonded carbons. This one would have like 2, just like that. Carbon here, carbon there. This would have 3. 1, 2, 3. This would have 4. That's it. This would have 5. Right? 1, 2, 3, 4, 5. This would have 6. This would have 7. This would have 8. All single bonded. Those are alkanes. Right? All these are carbons, and then the hydrogens fit in there. The way you figure out the hydrogens is you take the number of carbons, add 1 and double it. So 2 plus 1 is 3 times 2 is 6. So the format here would be, this would be N, and H would be 2 times N plus 1, or 2N plus 2. And you get the series of alkanes. I'm kind of jumping ahead. But if we make one of these a double bond, any one of them, or 2 of them, it doesn't matter. Then we have an alkene. And these are considered functional groups when you have this double bond, because you have an electron-rich bond. That pi bond makes it electron-rich, which makes it susceptible to compounds with carbons on them or some element on them that is electron deficient. So that's where the electrons are going, where they reside in their most stable form, and then how they get together is that positive and negative. So alkene, if we make a triple bond, that's an alkyne. Okay.
Which one is it, the model you just kind of wrote here where they're all single bonds? What's that one?
That's alkane.
Okay.
Yeah. If we do like that, and then this one would be like this. This one would be like that. Like that. In fact, acetylene, when we had acetylene before, we had 2 carbons, and then our hydrogens here. This is derived from ethane, would be the single bonded one. But since it's a triple bond, we change that to ethyne. So the proper name for acetylene is ethyne. Functional groups. Okay, alkenes, alkynes, aromatics. Aromatics takes a little more doing to understand aromatics, but the prime example for an aromatic is benzene. And if you have an aromatic in your system, it serves as a functional group. Halides, in other words, you take a halogen of any kind, fluorine, bromine, iodine, and attach it to a carbon. That is a functional group. That halide is a functional group. Alcohols, if we take, if we go off here and say like that, Okay. This is butane. If we add an oxygen on, alcohol on the end, OH, this is now, oops, butanol. Always ends with OL. That's a functional group. If we take a benzene and add an OH to it, that's known as a phenol. So we have that, and we add an OH to it. That's a phenol. Right. You ever gargle the, let's see, what's it called? Or sore throats? Can't remember the name of it. You can either gargle it or you can get the spray. It's got phenol in it. Phenol has a tendency to deaden the nerves, so it stops the hurt. Let's see, other functional groups. Thiols, SH. If we put an SH instead of a OH, instead of an alcohol, it's a thiol, SH. Ethers I mentioned earlier. When you have an oxygen in the middle, right, and then a carbon on the end and whatever else, that's an ether. That's a functional group. We'll get a little more complicated with acetals. Let's see, I need to make some room here. The acetal has, has carbon somewhere in the molecule like that. And you have two oxygens bound on either side. And then off of that, you have some group. Right, we use R's because there's no element in the periodic table that's R. That's an acetal.
Would
Yeah.
Sorry.
Yeah.
Would just be just some random element. The R represents.
Not just an element. It could be another carbon chain. Yeah, usually is. If, however, we change one of these to a hydrogen, now it's only got this side left. It's a hemiacetal or a half an acetal. Epoxides. If we have carbons in our chain, and then we have this like that, that's an epoxide. They're very, very unstable. We'll learn about why later. Amines, if we have a carbon and a nitrogen with something here. It could be hydrogen, it could be a methyl group, it could be some other carbon chain. That's an amine. Nitrile. If you have a carbon to a carbon, and then you have a triple bond to a nitrogen, that's a nitrile. These are all functional groups, and they're useful for promoting certain types of reactions.
Should we memorize these?
You ought to know, yeah, most of them. Yeah. Maybe make flashcards. Now, that's the way general chemistry students learn their symbols. Okay, make yourself a set of flashcards. And I tell them you don't have to memorize the whole table. So I give them a periodic table where the ones I want to memorize are marked off, about half of them. And I say, make yourself flashcards. That's the first step to learning them. And then flash the cards. Just drill them.
That's how I did the polyatomics.
Yeah. If you have a, let's see, if you have a carbon, let's see. Yeah. And it's connected to a carbon and then something else. And then this carbon has a double bonded oxygen. That's a ketone. Everybody knows nail polish remover, acetone. That's acetone. It's a ketone. Aldehyde. Aldehydes usually occur on the ends of molecules. So you have this long, you could have a long string of carbons or a short string, it doesn't matter. But once you get to the end of the molecule, then you're going to have an oxygen and a hydrogen. That's an aldehyde. Okay? Aldehyde. The simplest aldehyde is formaldehyde. And formaldehyde is going to have 1, 2, 3, 4. That's formaldehyde. Right. You ever taken a biology class where you had to do dissections? No? Oh. That's what you'll smell because they preserve your cadavers or your, not cadavers. Beginning biology, it's like, I don't know, fetal pig. It's going to be preserved with formaldehyde. And you get that smell in your face, you never forget it. If we take that carbon, and in addition to, we replace that oxygen and put place that hydrogen, put an oxygen in between there like that. Now we get a carboxylic acid. And it is an acid. This is that's the culprit that gives you the acid. That proton leaves the molecule and changes the balance of hydrogen and hydroxyls in water and gives you an acidic solution. Let's see, what do we got left? Ester. If you have a reaction with a carboxylic acid and an alcohol, like that, then what can happen is this hydrogen and that hydroxyl produces water. And you get a bond there. That's called an ester. You know what a true fat looks like? No, you haven't covered that in any of your courses. Okay. A true fat is a triglyceride, a triester of glycerol and 3 fatty acids. And they form this bond in 3 places on the glycerol molecule. And then the amide. Okay. We had the amine before. Like this. Yep. Before we had the amine like that, where it's just hydrogens. But if we replace the hydrogen with an oxygen, you have an amide. Instead of an amine, now you have an amide. And there are a number of polymers, plastics, that are formed by making this bond. In fact, proteins form that bond. It's a special kind of bond called a peptide. But it's basically an amide, a polyamide. The most famous polyamide is nylon. It was invented, I think the person's name was Carruthers. He was working for DuPont back in the 40s and came up with nylon. He just took an amine with an amine on both ends of the molecule and a carboxylic acid on both ends of the other molecule, put them together, and they form this amide bond in endless chain, made nylon. And that's what we made our parachutes out of, because we having trouble getting hold of silk, right, because of the war. Anyway, those are the functional groups. Most of them, common functional groups. There are others, and we'll call them up as we need them. All right. This won't take too long. I don't want to go into too much detail because if you ever take biochemistry, then, well, actually, if you take biochemistry, you're going to need both or organic chemistry 1 and 2. So I'll give you something.
I have to take, organic chemistry too.
No.
But I have to take biochem.
Really? Well, you may have enough information to do that. Yeah, it's possible. So there are 4 major classes of biomolecules. These are what you will find in cells. One is proteins. Right? They're made up of, they're polymers that are made up of individual amino acids. We'll talk about that later. Yeah, proteins, and I'm going to keep them in order. Carbohydrates. From the name, there's carbon, and there's hydrogen, and the ATE ending on this word is an antique way of saying oxygen. So they have carbon, hydrogen, oxygen. And nucleic acids, like DNA and RNA, they're also polymers of nucleotides. And then lipids. Lipids are, typically think of lipids as fats, but the category actually is expansive beyond fats. True fats, yes, but you can have other molecules that serve a specific purpose that are lipids. They're generally not water soluble. They're hydrophobic. All right. So here's the way proteins are built up. There's that amide bond, which is, in this case, a peptide bond. So you see the 2 carbons, and you see the amino acid. We have a carbon in the middle. Then we have some group over here. And you also have, off of this carbon, you have an amine group. They call this a primary amine because it's only bonded to carbon, nothing else. If it's bonded to 2 carbons, it would be a secondary amine. If it's bonded to 3 carbons, it's a tertiary amine. And then we got another carbon here, which is the acid group. So this is the amino part, and this is the acid part, amino acid. So they always have this central carbon. Then you have the carboxylic acid functional group and the amine group, and then something over here. This is where the uniqueness of each one comes out. This part right here. The bonding takes place between this group on one amino acid and this group on the other amino acid. So what you get is a chain of 1, 2, like that. And then, let's see. Right next to this one, that's carbon with that double bond. And then, let's see. Then that 3 carbon. And then, oh, excuse me. I'm getting confused now. Let's put 2 amino acids out here and link them together. That'd be better. So we have this R to that one, and this one, NH2, and then this one to oxygen and OH. Okay. Then we put another one over here, and these can be different. Usually are. And this one has a carbon there with an amine group. And then we have this oxygen here. And we're going to form a dipeptide. Just 2 amino acids. What you have is this OH and that H make water. Then you have the bond between this carbon and that nitrogen. That's called dehydration synthesis. Whenever you remove a water to form a bond, that's dehydration synthesis. And you can chain these together forever. This can react with another amine group, and it just goes. Some proteins are just huge molecules. I would think that molecules in your muscles, your skeletal muscles, would be very large. All right, there's your amino acid. Right, you got the central carbon, what they call the alpha carbon. And then you have the amine group on it, and you have the carboxylic acid group on the other side, and then you have the R group. So you always have the amine, carboxylic acid, a free hydrogen, and the R group. Now, if the R group is another hydrogen, you have the simplest amino acid that you think of. It's called glycine. Now, here's some of them. So there's your glycine, right? The middle top, where the R group is H. If the R group is another methyl group, that's alanine. That's relatively simple also. And then there are others. I'm not going to have you memorize those because that's for biochemistry. I will say this though. Remember this, put this in the back of your mind. When you have this amino acid and this carboxylic here, and that R, let's see, there's another hydrogen here, right? 1, 2, 3, 4. We're going to talk about this again in stereochemistry. When you're talking about how can you draw this molecule different so that everything's connected the same way, but it's not the same molecule. It's a chiral center, we say. In other words, my hands like that, I can't overlay them, right? They're mirror images of each other, but they're not identical. They're different. That's a chiral center. Chiral comes from the Greek for chiro, which means hand. But when this is any other group, then that is a chiral center. In other words, you can have handedness. You can have a different molecule depending on how they're attached. But if this is hydrogen and that's hydrogen, you don't have a chiral center. That's true for glycine. Only glycine is not chiral ever, whereas the others are.
Can you spell that?
Oh, chiral. CHIRAL. We'll talk about it in more detail later. Got to need a marker. That one's getting a little thin. Okay. Oh, while I'm thinking about it, do y'all have lab coats?
We have lab aprons
Yeah, that'll work.
involved.
I've got eyewear, unless you want to bring your own. Yeah, if you found something that's comfortable, right? You don't have to wear goggles in this class. I've got polycarbonate wraparounds. You can actually wear them over your glasses if you, like me, and wear glasses. But they're more comfortable than goggles. Okay. So these on this page and on the next page, these are the naturally occurring 20 amino acids naturally occurring. You're going to find those in your body, making up your proteins. And they act differently, right? Because these R groups are kind of, there's the chain, and these R groups are kind of sticking off the sides. And that's where you get the action with those functional R groups. That's why this protein is different than that protein, because it's got a different arrangement of those, some of those 20 amino acids. carbohydrates. Carbohydrates are, they can be very simple, they can be very complex, right? The simplest carbohydrates, we call them sugars. Right? Or let's see, I forgot the proper word. It'll come to me later. But they're basically carbon chains with hydroxyl side groups. That makes them very soluble in water, right? Because if you've got a chain, 1, 2, 3, 4, 5, 6, and each one of these positions has a hydroxyl. It has hydroxyl. That's a potential hydrogen bonding source right there. Remember, oxygen and hydrogen. So when water comes in here, it can make a very strong intermolecular bond with these hydroxyl groups, and that makes sugars very, very soluble. In other words, if you make up hummingbird food for your feeder, you usually put what, a cup of water and a cup of sugar together. I mean, it goes into solution faster if you heat it, but eventually, I mean, just put it in there and stir it up. It'll eventually all go into solution. Well, you should know that you can put 2 cups in there and it'll go into solution too. So eventually you'll have more solute in there than you had solvent. That's because of the very strong attraction, the hydration of the sugar molecules with water. Okay. There are various types of these sugars, these simple monosaccharides. Monosaccharide just means one sugar. Our example, one of the examples there is, well, ribose, of course, is part of the RNA, ribonucleic acid. So riboses are in there. But glucose is what your body uses to send energy various places through your bloodstream, right? And if you're not diabetic, when it gets to a cell, it goes in the cell, cell chops it apart, gets energy from it, and does its thing. If you're diabetic, then that glucose can't get in the cell. It won't go in the cell. And it builds up in your bloodstream. So my wife has one of those things in her arm. You just hold her phone up to it with the app and it reads her blood sugar. She doesn't have to prick her fingers. But controlling your blood sugar requires injections of insulin substitutes. She's got 2 types. One is fast acting, one is long acting. But this glucose molecule circulates and it's C6H12O6. Now, if you just write C6H12O6, that doesn't tell you anything about the structure of the molecule. Right? This could be glucose if it has that structure in the middle. But notice it's got it's an aldehyde functional group on the end of glucose. Right, so we would change this to oxygen, just like that. And if we wrote it correctly, that would be glucose. But if we move this aldehyde and made it into a ketone, you've got the same molecular formula, but you've got a different molecule. You've got fructose now. Glucose and fructose both have 6 carbons, but the position of that, I'm trying to remember my terms. If you move that over here, then you've got a different molecule, and it reacts differently. Tastes different too. Right? If you have cane sugar in your drinks, they taste different than the high fructose corn syrups. I mean, they might be as sweet, but there's a difference in flavor.
So the difference here is, I'm assuming just what's highlighted? Or no?
But, well, from between these two,
Yeah.
you move that, double bonded oxygen, carbonyl, the carbonyl group, move it from here over here. Right, put the OH back over here and put the ketone here. And that changes the function of the molecule. I don't know if you've ever had the original Coke. You're probably too young to remember the original Coke. It had a good flavor. And then they decided to go new Coke, and it bombed. Right? Nobody would buy it. So they went back to Coke Classic. And they claimed that it was the same formula as the original Coke, but it had a different sugar content. It had high fructose corn syrup, not glucose. Not sucrose. Sucrose is a disaccharide. It's fructose bonded together with glucose. That's table sugar. It has a different flavor than the high fructose corn syrup. You can still get that original formula, but they only make it in Mexico. So if you see Coke in bottles and you look on the thing, it says product of Mexico. Yeah, it's got a good flavor. They have it at Sam's Club sometimes during the holidays, and then they go away. Okay, so those are monosaccharides, are these sugars that are either the aldehyde groups, aldehyde types, or the keto types. And there's a whole bunch of them. The thing about these, we drew them in a straight chain form, but what tends to happen is the head of the chain reaches around and forms a bond with the tail. And that's what's happened here with this form down below. That glucose molecule has the aldehyde group on the end, and then it reaches around and forms a bond with the carbon of the other end and forms that structure. Now, it opens and closes. Right? Sometimes it's straight form, sometimes it's a cyclic. And that's what those double arrows are saying. It goes back and forth between the two. Now, what you can also do is, once it's in the cyclic form, you can form a bond between this one on this molecule and that one on the other molecule. Right? Form that linkage. And that, if you just have two of them, it's a disaccharide. You got two sugars, or three trisaccharide. Or if you have a lot of them, a polysaccharide. Now, the most common polysaccharides come in two flavors. One is starch, which is very easily digestible. It's based upon the way this thing is flipped when it bonds. Right? It forms an alpha linkage, we call it. Those are easy to digest. So if you eat a high starch diet, you're going to flood your system with glucose. And that's when, if my wife wants to eat pasta, I get out the syringe and give her 15 units before she eats. But if the bond is the other way, the beta bond, we call it, the beta bond, our enzyme systems can't break it. Right? So that's what we call fiber. It goes in one end, comes out unchanged the other end. It's a bulking agent. And that forms cellulose. It's the primary component of woody plants. It takes a special enzyme system to do it. Termites can do it, but it's not the termite that does it. It's a symbiotic microorganism in their gut that does it. Okay, polysaccharides. Nucleic acids. The nucleotide has three components. It has that ribose component on the bottom. So that the ribose that we saw in a chain now has the aldehyde has gone around and formed a 5-member chain with oxygen at one of them and 4 carbons. And then it's bonded to a nucleoside. Nucleic acid, excuse me. The nucleic acid. The one with all the nitrogens in it. Okay. And then the ribose also is bonded to a phosphate group. That's a nucleotide. And then you can form long with the phosphate and ribose as the backbone. All right, so the phosphate will form a bond with a neighbor ribose. So you'll have ribose phosphate is the backbone. And then these nucleic acids sticking out on either side.
Why is there H phosphate? That hydroxide?
Yeah.
Why is there an H?
Because it's an alcohol group. Yeah. If we, let's see. We learned the polyatomics this way, right?
Yes.
Like that. Okay. If we write that out, let's do the Lewis structure. Right. Where's phosphate? Does that have 5? Is that 5 valence electrons?
For which one? For P?
Yeah.
Yes.
Okay. So that's 5. That's 6. That's 24 total there, plus 5, plus 3. So that's 32, right? So if we put this in the middle and oxygen's here, 2, 4, 6, 8, 24, 2, 4, 6. 6 times 4. That uses them all up. We do that. Okay. Phosphorus already has an octet, except it tends to exceed the octet. Right. So we'll do something like that. And then we have to include the charge. And let's see. Oh, we left out, well, if it were phosphoric acid, we'd add the hydrogens. So we need 3 hydrogens. So if we did this, then we do away with the charges. We had a hydrogen there, we had a hydrogen here, and we had a hydrogen here. Then that would be phosphoric acid as long as it's aqueous. But in this case, we removed one of the hydrogens and bonded one of the oxygens. So this one's bonded to the ribose. And this one, let's see, this side over here. This one's missing the hydrogen, which left behind these. That makes it a single negative charge. That's the phosphate group. Phosphates are extremely important in biochemistry, in the functioning of cells. And I can sum it all up in one acronym, ATP. Okay. Nucleotides, right, they're made up of this. I said nucleic acid. This is a nitrogenous base. These things right here. So they have those 3 components. They have the sugar, they have the phosphate, and they have the nitrogenous base. That's a nucleotide. And then we string those nucleotides together to make DNA or RNA, depending on whether it's ribonucleic acid or deoxyribonucleic acid. There you go. So for DNA, we have guanosine, adenine, cytosine, and thymine are the nitrogenous bases that are part of the polymer. And for RNA, the sugar is ribose instead of deoxyribose, plus instead of, let's see. Thymine, uracil is substituted for thymine. That's the difference. So thymine is substituted for uracil on the other end. And the only difference between the two is that methyl group. Right? Uracil doesn't have that methyl group on it. Now, I don't know why. It just is. Right? Why would it be that way? Well, maybe by using uracil in there, the cell is able to differentiate between RNA and DNA.
We need to have this kind of thing memorized.
No, I don't think so. If by some chance I put questions like this in the homework, go ahead and try to work them. You may need them later anyway. Okay, that takes care of chapter 1.